Okay, today we're going to talk about section 9.6, mathematical induction. This is a brief introduction to mathematical induction. It's a proof technique, and you might be wondering why we're looking at this game, Tower of Hanoi. It's an old game, and we're going to talk about it, and it's going to come back up later. But how this game works, um, I'll post a link to this in there if you want to try it. But the idea is there's a pattern to the minimum number of moves. You can see here we've got 3 discs here. It says minimum moves is 7. Okay. With this game, you must move all the pegs from the leftmost, or all the discs from the leftmost peg to the rightmost peg without ever setting a bigger one on top of a smaller one. So I'm going to demonstrate this with 3. So far that's 3 moves, 4 moves, 5 moves, 6 moves, and 7 moves. Okay. Turn up the discs to 5. Let's go 6. This might take a bit longer, but having to put a little bit of thought into this so that I don't go to the wrong side. And if you'll notice my process, I'm stacking them. And it takes a little bit to get used to the idea. Of where do I need to go? Now I need to think for a second. And so kind of a little bit of a pattern game. And so the formula for this, if I call n my number of disks, the minimum number of moves is equal to 2 to the power of n minus 1. 2 to the 6th is 64. This one was 63. 2 to the 6th minus 1. Okay, so that's going to lead us into this process of adding and moving on and kind of this recursive process of mathematical induction. And mathematical induction has 2 steps, but we're going to make it 3. The book kind of makes it 3, and I want you to make it 3, 4, because it's very easy to forget the second one if you make it 2. And in the future, if you go into a lot more math, you'll do more of this, where you'll probably do it as 2. This book calls the first step the anchor. A lot of places or a lot of professors will call it the base case. In the base case, you prove that it works for the first one. Number 2 is going to be the inductive hypothesis. This is often included in step 3 as you get further along. But since you're first doing it, I want you to make it its own step. In the inductive hypothesis, you assume that it is true, your statement of recursion, and you prove it is true for the next one. Or, well, you assume, that's the inductive hypothesis. The inductive step is you prove that it must be true for the next one. And this works with all sequences. Okay, let me explain why. If you prove the first case is true, you can assume that the first case is true. You will use the inductive hypothesis in the inductive step always, but if you prove the first case is true and you prove the next one is true, well, the next one from the first one is the second. If you've just proven that's true, so now if you've proved the next one, you've proven the third. If you prove the next one, you've proven the fourth. And if we've proven as many, we arbitrarily we can assume that the 10th one is true. Now we prove the next one's true, that's the 11th. So you must have this base case or this anchor to start with, okay? Because you're proving the general next one is true, you need a first starting place, because the next one after 1 is 2. And if the next one is always true, you can, and the first one was true, you know it should be true for all of them. So, using mathematical induction, okay? This is example 1. So, we're going to prove that this series adds to, I don't want that one, adds to n squared. So, number 1, my anchor. So, with my anchor, 1 is the left side, and it does equal 1 squared. That is true. Okay, one thing with the inductive hypothesis. We are going to, because we are trying to prove that it's true for n, we're going to assume it's true for k. So we're picking a different variable, and that's important in formal proof technique. So we are assuming n equals k, because we can't just assume our statement. So we're going to assume it about k, assume if n equals k, then oops, I don't know why I wrote plus twice. So now I'm at 2k minus 1. Should probably put parentheses around that. That's its own term here. So I'm assuming my statement is true. And again, the reason I can do that is I know somewhere along the line the first one's true. So what I'm doing is proving the next one. And if in general I prove the next one, it means everything along this will be true up until the point I've gotten to, and then inductive step. Some places will do this with assume k minus 1, but we're going to assume it for k. So the inductive step, in place of k, we plug in k plus 1. So in place of k, I plug in k plus 1. And this, some books won't let you show what you're trying to make. Essentially, I am trying to make this show that this equals k plus 1 squared. So my goal is to get to parentheses k plus 1 squared. And it's always good to have this. This doesn't go in the formal proof, though. So this part right here equals k squared by inductive hypothesis. I assumed that's true. That means I can use it. And then this last term I'm going to distribute. So 2k plus 2, and then I got a minus 1. Now I'll combine my 2 and my minus 1 to be plus 1. And that factors into k plus 1 squared. So since the equation is true for n equals k plus 1, so now if I've changed n to k plus 1, if my new n is the next term, k plus 1 term, it must be true. So I can say, thus I have proven, and this is an important statement, by the principle of mathematical induction. So there's kind of three key things for math induction. Your anchor or your base case, your inductive hypothesis, and your inductive step where you use your inductive hypothesis. Okay, that's all the inductive step. You don't necessarily have to specify your inductive hypothesis as well as I did, but it should be there, and you may want to notate it for yourself. So example 2. Okay, so we're going to prove this by mathematical induction. So we're going to start with our anchor. Which is equal to 1 times 2 times 3 over 6, which is 6 over 6, which equals 1. My inductive hypothesis, assume, oops, I should have written out, number 2 is inductive hypothesis, I didn't write it out. It's okay, I probably need the space anyways. Assume that, oh wait, for n equals k. K squared three, my inductive step, so now I'm going to do this for k plus 1. Plus k squared and again, my goal is to get to plugging in k plus 1. So again, I plugged in k plus 1 for the k's. And I do actually need to get back to show that. Which when I simplify this out is k plus 1 times k plus 2, 2k plus 3. That's what I'm trying to get. My inductive hypothesis is that this is going to be that. So I'm going to start right away and substitute that in. And then I'm going to take k plus 1 squared, and I'm going to square it. Okay, so k plus 1 times k plus 1, it's k squared plus 2k plus 1. I'm going to need a common denominator here, which means I'll multiply that by 6 over 6. This next step, I'm going to start by expanding this out. 2k squared, let's do k, 2k squared plus k plus 2k is plus 3k plus 1. That's over 6. And 6k squared plus 12k plus 6 over 6. Now I'll multiply my k in. K cubed plus, no, 2k cubed plus 3k squared plus k, 6k squared plus 12k plus 6, and they're both over 6, so I can make them a single thing over 6. Now I can combine like terms, 2k cubed plus 9k squared plus 13k plus 6 over 6. So now I want to factor my numerator, which I'm going to divide by 1. So functionally what I'm doing is polynomial division. I'll use synthetic division to do this. But I'm going to actually divide by k plus 1 and then k plus 2. So remember, in my box goes the solution to k plus 1 equals 0, which is -1. Two, -2, 7, -7, 6, -6, and that is 0. I'll do the same thing with -2 for k plus 2, because I don't feel like factoring it the other way. So I think this is going to be the quicker way to factor. 2, -4, 3, -6, 0. So after synthetic division, I know k plus 1 was a factor. I know k plus 2 was a factor. And I'm left with a 2 and a 3, which means 2k plus 3 all over 6. And that's what I have right here. I'm supposed to have what I have over here on that left blue statement. And so I'm going to change it to that, because I know it factors one way that way. So it's got to factor back the other way. K plus 2 is k plus 1 plus 1. 2k plus 3 is 2, parentheses k plus 1 plus 1. And then I finish up with, thus by mathematical induction, thus by the principle of mathematical induction. This statement that I started with is true. Okay, so this is example 3. We're going to prove divisibility. Okay, so we're going to use it math induction to prove that 4 n minus 1, so n being integers for any sequence, is divisible by 3. You can write this is the fancy notation, 3 divides, what this vertical line means is divides 4n minus 1. That means evenly, that means no remainder. So to do math induction on this, that means essentially 3 can factor out, okay? So we start with our anchor, or our base case. Depends on who you're doing this for. And that means 4 to the first minus 1. That equals 3, and 3 divides 3. Inductive hypothesis. Assume they write it a little bit differently than I do sometimes. P sub k is true. So 3 divides 4k minus 1. Oops, the minus 1 is not part of the exponent. So inductive step, I'm going to show it for k plus 1. And that means I'm just going to have factor out of 3. So here I've got 4k plus 1 minus 1. So that means 4, let's see here. This equals 4 times k times 4k times 4 to the first. That's using my exponent rules that I add these exponents k and 1 to get k plus 1. Now I'm going to do a little bit of creative manipulation, which means I am going to add a 4 here. No, not exactly. That's not how I want to show this. Which I could make this 4 times 4k minus 1. And I'm trying to use this 4k minus 1 here. So if I factor out a 4 from this, I get a 1/4. That's not helpful. But let's say I add a 4 here. Now let's add a 3. Okay, so never mind. If I do this, that is equal to 4k minus 4, right? It's equal to 4 times 4k minus 4. So essentially, I'm doing minus 3 here, plus 3. Well, let's do that in a different color. That's minus 4. So this is equal to what I'm trying to get, 4. That's equal to 4 times 4k minus 4. So if I do minus another 3 plus 3, this line here is 4 times 4k minus 4 plus 3. That translates into that. And then I have a plus 3 here. Now, since if 3 divides 4k minus 1, 3 will divide 4k. Or no, 3 will divide 4 times 4k minus 1. Because it's just 4 times some factor. And 3 divides 3. So since it divides both these pieces, piece 1 here, 3 divides that piece, and 3 divides this piece, piece 2. 3 has to divide the whole thing. which that whole thing started as 4k plus 1 minus 1. So I can say that 3 divides my original thing by the properties of math induction. Property, let's not do properties. Or not property, principle. Sorry, it's the principle of mathematical induction. Again, what did we do here? We proved that it worked for the first one. And then I proved in general that it works for the next, no matter what the next is. So I assumed it works for the current. That current could be the first. If it works for the next, the next is the second. Now I've proved the second. I can use that to justify the third. Anything becomes current because the next one always works if the first one works. Okay. Before I finish this up, we're going to talk about 2 types of reasoning. There's inductive reasoning. Inductive reasoning, we use evidence derived from specific examples to make general conclusions. So we've got a whole bunch of specifics. We've seen this evidence in maybe this lab or this lab or this lab or this place in life, this place in life, this place in life. And then we draw a general conclusion. Okay. Deductive reasoning, on the other hand, takes general principles and draws conclusions about specific cases. Good, strong deductive reasoning will draw conclusions about specific cases that have never been had conclusions drawn about them before. Okay, that's good, strong deductive reasoning. Okay, that is the end of section 9.3.